Old Grumpy Hunter here. Welcome to part 3 of this series. A series that I had not planned to do, but this series, as I predicted in Are You Thinking of Taking the 100-Yard Shot, has turned out to be controversial. I hear the screaming, the gnashing of teeth, and the sound of people running away. But yet the series is based on the laws of physics that cannot be violated. Someone commented on the video, momentum versus kinetic energy and other things cannot add mass without dropping kinetic energy and raising momentum due to the fact that the speed will always drop as the arrow's weight increases. That statement is correct, and it's wrong at the same time, but we'll get back to that later. In the first 2 videos, Are You Thinking About Taking That 100-Yard Shot? And momentum versus kinetic energy and other things, I touched on arrow weight and hit kinetic energy hard. For the most part, everyone knows and agrees that a heavier arrow will penetrate the target better than a light arrow. Both bow manufacturers and manufacturers of arrows advertise how fast their product is. They go on and on about kinetic energy with pride that the fast arrow generated. After all, it is the velocity factor in the kinetic energy formula that gives us dramatic increase to the calculated kinetic energy delivered by an arrow and broadhead combination. In theory, the more kinetic energy you have, the more penetration you will have. But that is not so. I can see the eyebrows raising right now. Many of you have seen the videos where the bucket or buckets of sand are shot with both a rifle and a bow. Which one has more penetration? The bullet shot from the rifle has much more kinetic energy than the arrow, but what happens? The arrow goes through, but the bullet stops. How can this happen? While kinetic energy calculated on paper is great, there are several other factors that influence the results. In the case of the sand-filled bucket, the sand plays a huge part in penetration. Furthermore, the momentum of the arrow and bullet, along with their shapes, are the primary factors on how well the bullet or arrow will penetrate. In reality, you cannot measure the amount of penetration with sand, plywood, steel, or even meat and bone unless the meat is fresh. It's even better if it's alive. By now you're asking, if kinetic energy is not how to predict penetration, why do we need to know about it? Well, kinetic energy is critical to understanding how bullets act when hitting an animal. Because the bullet's high velocity, it causes the tissue on contact to accelerate to the same speed as the bullet, causing enormous temporary wound channels and dramatic shock effect to the animal that's struck by the bullet. The high rotation speed of the bullet causes the surrounding tissue to be thrown away, much like a spin cycle of a washing machine throws the clothing to the sides of the washer. Together, these 2 actions cause hydrostatic shock, but that's a topic for another time. As bow hunters, we know that it is the cutting action of the broadhead causing massive bleeding and not shock of the impact that kills the deer. To cause this massive bleeding, the broadhead must penetrate into the vitals of the deer. So what causes the penetration? Inertia and resistance. As stated in the momentum versus kinetic energy and other things video, Newton's first law of motion states an object at rest stays at rest and an object in motion stays in motion with the same speed and direction unless acted upon by a force. Objects have a natural resistance to change of their state of motion. This resistance to change a state of motion is inertia. To understand this better, you need to know a few more terms. Acceleration. Acceleration is the rate of change of speed of an object, or how much the velocity of an object in motion changes during a specific period of time. The acceleration of gravity is expressed in feet per second. This determines how many feet per second the velocity changes as each second passes. Impulse. Impulse is a force of momentum applied over a unit of time. Net force Net force is the total amount of energy exerted by an object in motion. It is the change in momentum divided by the change of time. Impulse is extremely important in the study of momentum and to the understanding of penetration. When a force is applied to an object, time passes. We can say that the impulse was applied to an object. For example, when an arrow is launched, an impulse is applied to the arrow. For a short time, the bow applied force to the arrow. Newton's third law of motion states forces always come in pairs. The arrow puts a force on the bow, therefore the bow also has had an impulse applied to it. The mass of a moving arrow does not change in flight. That creates a net force equal to the momentum times change in velocity divided by flight time. Force equals mass times acceleration. Impulse is the net force of an object times the period of time over which the force is applied. Mathematically, it is force equals mass times a change in velocity divided by a change in time, or F equals m times change of velocity divided by the change of time. Using some algebra, the formula is rearranged so that the force times the change of time equals mass times the change in velocity, or the change of impulse equals the change in momentum. Because of all that, the arrow has a given momentum at a time of impact with the animal. At that instant in time, the arrow decelerates. If the arrow stops in the animal, the arrow's net force has been used up between the moment of impact and the time of when it stops. The arrow's velocity will have changed 100% from the time of impact to when it stops moving. The impulse on the tissue equals the velocity of impact times the time it takes for the arrow to stop. The resistance of the tissue to the penetration of the arrow from impact to time of stop is the tissue's impulse on the arrow. Both impulses will be the same. When an arrow has passed through, the impulse applied is the momentum at impact minus the momentum of the arrow at exit for the length of time it takes the arrow to pass through. Because the mass of the arrow has not changed as it went through the animal, the net force decreased by proportion to the decreased velocity while the arrow is moving inside the animal. Force is proportional to the rate of change of momentum. Comparing two arrows, one is light and fast while the other is heavy and slow. The heavier arrow will have greater impulse force because it takes longer to stop. This is because of Newton's first law of motion. It is the inertia of the arrow that makes it want to keep moving. The more mass of an object gives to momentum, the harder it is to stop. Now, those archers that use light, fast arrows will say that their arrows will travel farther through an animal for a given time than the heavier, slower arrow. That cannot happen because it would violate the nature of resistant forces. As velocity increases, the resistance does not increase at the same rate. In fact, it increases exponentially. In other words, if the velocity doubles, the resistance increases 4 times. If the velocity quadruples, the resistance of penetration is 16 times higher. Try holding your hand out the car window at 30 miles an hour, 44 feet per second, and then do the same at 60 miles an hour, 88 feet per second. The car's speed is only doubled, but the air resistance is quadrupled against your hand. All momentum is not created equal. Since tissue is much denser than air, the tissue has a higher resistance to the passage of an object. To help understand this better, I'll compare two arrows. The first arrow has a velocity of 150 feet per second, and it has a weight of 700 grains. The velocity of the second arrow is 300 feet per second. It weighs 390 grains. The slower arrow has a momentum of 0.47 pound-seconds and a kinetic energy of 35 foot-pounds. The faster arrow has a momentum of 0.52 pound-seconds and a kinetic energy of 78 foot-pounds. Remembering that the increase in resistance to the tissue is based on the velocity of the arrow. The heavier arrow has about 10% more disposable net force and about 123% more kinetic energy than the lighter arrow, but because of the higher velocity is met by 4 times the resistance to penetration. Thus, the slower, heavier arrow will out-penetrate the faster one. What if momentum of the 2 arrows is the same? Taking 2 arrows that are equal in all features other than the mass, and both having the same momentum, the arrow with the greater mass will have the greater penetration. Newton's law makes this true. Arrow 1 is 350 grains and has a speed of 400 feet per second. Arrow 2 is 400 grains and has a speed of 350 feet per second. Doing the math, we find that the momentum is the same, but the heavier arrow has 114% more kinetic energy. The arrow with the higher velocity will be met with more resistance. To get a better hold on mass and momentum inertia, think about the time you pushed a car, and once it started moving, it was hard to stop. The car's mass, even at a slow speed, had a great momentum. Using a 2-ton car moving at 1 mile an hour, it has a momentum of 182.2 pound-seconds. One factor I don't have any data on is resistance caused by the broadhead and its design. Certain types of broadheads penetrate better than other ones. Broadheads with a cutting tip have less resistance to broadheads that don't. Furthermore, the width and shape influence penetration. A long, skinny broadhead will penetrate more than a short, fat one. Mechanical broadheads that open on impact may fly like field points, but the resistance they encounter upon opening in an animal is considerable. Furthermore, they require more momentum to have the same penetration as a fixed blade. By now, either 1. You have gone to sleep, 2. Shut off the video, 3. Are wondering what this has to do with the increase in arrow weight. I'm really hoping that you pick number 3. When you increase the arrow's mass and are using the same bow, the initial speed of the arrow drops, but by how much? For every 5 grains of arrow weight change, there is approximately 1 foot per second change in speed. If you add 5 grains, the speed goes down 1 foot per second. If you remove 5 grains, the speed goes up 1 foot per second. Using a bow that shoots an arrow that weighs 400 grains at 400 feet per second, by increasing the weight to 450, that will result in a new initial speed of 390 feet per second. Even though the velocity decreased, the momentum went up. The momentum changed from 0.71 pound-seconds to 0.78 pound-seconds. At 30 yards, the 400 grain arrow has a speed of 386 feet per second, and its momentum is 0.69 pound-seconds. The 450 grain arrow has a speed of 378 feet per second, and its momentum is 0.75 pound-seconds. So what does this mean? The heavier arrow with its slower speed will have more penetration when it hits because it has more force. Remember, F equals ma. Getting back to the comment, you cannot add mass without dropping kinetic energy and raising momentum due to the fact that the speed will always drop as the arrow's weight increases. As I said before, that statement is both correct and it's wrong at the same time. What's definitely correct in that statement is when you add mass, you increase momentum, and the arrow slows, and there is a point where kinetic energy starts to drop. Using 2 arrows I just spoke of, let's run the numbers. I'll start with the initial speed of both arrows. The first arrow has a kinetic energy of 142 foot-pounds, and its momentum is 0.17 pound-seconds. The second arrow has a kinetic energy of 151 foot-pounds and has a momentum of 0.78 pound-seconds. At 30 yards, the first arrow's kinetic energy is 132 foot-pounds, and its momentum is 0.69 pound-seconds. The second arrow has a kinetic energy of 143 foot-pounds, and it has a momentum of 0.75 pound-seconds. At what point does the comment in question become true? You will have to add an additional 885 grains to the arrow to make a total weight of 1,285 grains. The resulting initial speed would be 223 feet per second, producing 141.9 foot-pounds of energy and 1.27 pound-seconds of momentum. Is a 1,285 grain arrow practical? So why do you have to more than triple the weight of the arrow before the kinetic energy drops? Remember, in the kinetic energy formula, velocity is squared. In summary, Newton's laws of motion cannot be violated. Objects have a natural resistance to changes in their state of motion. Energy comes in pairs. Increasing the mass of an arrow will lower the arrow's speed when shot from the same bow. For every 5 grains of change of mass, the velocity will change about 1 foot per second. Increasing the mass will change both the momentum and the kinetic energy. At some point, the kinetic energy will decrease with added mass. Acceleration is the rate of change of speed of an object. Impulse is force over a unit of time. Net force is the total amount of force exerted by an object in motion. Kinetic energy causes damage, where penetration is the result of momentum. A bullet causes hydrostatic shock, where an arrow causes bleeding. More mass an object gives to momentum, the harder it is to stop. 2 arrows with the same momentum can have different penetration. An arrow with a higher velocity will be met with more resistance. A heavier arrow with its slower speed when shot from the same bow will have more penetration when it hits because it has more force.
Thank you for watching this Old Grumpy Hunter presentation. Please give it a big thumbs up, and if you haven't already, please subscribe to my channel and don't forget to push the notification bell.